Hello guys, welcome on Tesla Eduventures. In this video, we are going to discuss the parallel LCR circuit. It is also called as rejector circuit, and I would tell you why it is called as rejector, but this will be told in the later part of this video. So let us start with the video and let us see that let's suppose a current of I is incoming in the three elements of the circuit, and the current splitted in the resistance is IR, this is IL, and this one is IC. Now you can see that obviously we cannot write it down as I is equal to IC plus IR plus IL. This is wrong because obviously these currents are not in phase, so we cannot write them like this. So if we draw the phasor diagram, so let us draw the phasor diagram first of all. So this is a phasor diagram, and we know that in parallel circuits we always place the voltage on the reference axis. So the voltage will be placed on the x-axis, and this voltage will be same as the voltage across inductor, resistance and capacitor, because they all are in parallel. But we know that the current across the resistance is in the same phase as that of voltage, and the current across the capacitance is leading the voltage by a phase of pi by 2, and the current across the inductor lags behind the voltage by a phase of pi by 2. This we know. Now, obviously, we can say that we can, in fact, we are assuming that IC is greater than IL. IC is greater than IL, and therefore the resultant current of IC and IL will be IC minus IL on the positive y-axis. And the resultant of these three, IC, IL, and IR, will be on this axis like this, I, and I will be equal to under root of IC minus IL ka whole square plus IR ka square. This angle is phi. So tan phi is equal to IC minus IL upon IR. Okay, and we can also say that IC is equal to V by XC. IL is equal to V by XL, and IR is equal to V by R. Okay, so we have assumed that IL is greater than, in fact, we have assumed that IC is greater than IL. So this assumption is on the fact that we can say that XL is greater than XC, and XL would be greater than XC in the circuit which has a high input frequency. So we know that at high frequency the inductive reactance is greater than the capacitive reactance. Okay, so now let us say that tan phi is this one, and if we just write down IC as V by XC and IL as V by XL and IR as V by R, so we can write it down as R into XL minus XC upon XL XC. So this is tan phi, and tan phi will be equal to R into XL minus XC upon XL XC. This is tan phi. Okay, and obviously we can write down the time based equation of current as I is equal to I naught, and I naught can be written as V naught by Z sine, and this is omega t plus, because in this scenario we have assumed that the current leads the voltage, and this assumption is on the basis that we have assumed that IC is greater than IL, and IC is greater than IL only when XL will be greater than XC. Okay, so there are the basic assumption of this thing is this one, and therefore we are writing it down as tan inverse R into XL minus XC divided by XL XC. This is the value of current. Okay. Now let us see the scenario that if we talk about the resonance curve in this case, let us talk about the resonance curve. And we know that the resonance curve is always drawn between the current taken on the y axis. In fact, I naught, which is the peak value of current, is always taken on the y axis, I naught, and omega is always taken on the x axis. And let us find out the value of z first of all. And we know that z is I was equal to, I'll write it down here, that I was equal to under root of IC minus, or let us what let us do that, let us find out. Now if we discuss about the impedance, then we have to write down the current, and current was under root of IC minus IL whole square plus IR square. And current is equal to V by Z, obviously. And we can write down IC as V by XC, IL as V by XL, and IR as V by R. And V will be cancelling out V, so Z will be equal to 1 upon under root of 1 by XC minus 1 by XL whole square plus 1 by R square. Okay, this is the value of Z, which is the impedance of this parallel LCR circuit. Now, if we see the scenario, and if we now discuss about the resonance curve. So, resonance curve in this case will be drawn between the current I naught, and on the x axis it would be the omega. So this is I naught and this is omega. Okay, and if we start to discuss about z, and if we take omega as 0 initially, so xc will be infinity and xl will be 0. 1 upon xc will be 0 and 1 upon xl will be infinity, and therefore z will be infinity, and I naught therefore will be 0. So curve will start from 0 comma 0, as at omega is 0, I naught is also 0. Now when obviously you can see that 1 upon xc, this is 1 upon xc, which is 0, and this is 1 upon xl, which is infinity. Okay, and the gap between these two is also infinity. Now when omega is increased, then obviously 1 upon xc will increase, and 1 upon xl will, this is xl, yes, and 1 upon xl will decrease. So the difference between these two will decrease, and these two terms will come closer to each other. It will come closer to this and it will go closer to this. Therefore, Z will decrease. Okay, and if Z will decrease, I naught will increase. In fact, Z, this difference is decreasing, and we can see that Z is inversely proportional to this difference. So Z will increase, and Z will increase, then I naught will decrease. Okay, So this graph will start from infinity. It will come down like this, and then there will be a minima. And at this point, at minima, it would be resonance, and I naught will be minimum. And now we can discuss that at resonance condition, when omega will be equal to omega r, xl will be equal to xc, and therefore z will be maximum. Okay, because z is increasing with increasing omega, and at the point when xl and xc will be equal, 1 upon xc will be equal to 1 upon xl, then z will be maximum, and maximum z will be equal to r, and I naught will be minimum. So the minimum I naught will be equal to v by v naught by r. So we can write down I naught minimum as V naught by R. Okay, and this is the resonance condition. So it is very important to note that at resonance condition, at uh, at resonance condition in parallel LCR, when there is a resonance condition in parallel LCR, then Z becomes maximum and it is equal to R, and I naught becomes minimum and it is V naught by R. And circuit behaves like pure resistive circuit. Circuit behaves like pure resistive circuit. Okay, and this now, when if we will further increase omega, if we will increase omega, then the difference of XL and XC will increase, because now if omega is further increased, then 1 upon XL will decrease and 1 upon XC will increase, and therefore 1 upon this is XL, and therefore 1 upon XL minus XC mod, because it would be negative now, will increase, and Z will decrease, and I naught will increase. And when omega will be infinity, x 1 upon xl 1 upon xl will be 0, 1 upon xc will be infinity, and Z will be infinity, and I naught, in fact Z will be 0 and I naught will be infinity. So this curve will again go to infinity, like this. Okay, so this is a resonance curve in parallel LCR, and obviously you can see that in parallel LCR, if like we are using series LCR in radio receiving, and instead of series LCR, if we would have used the parallel LCR, then we can see that at the resonance frequency, the impedance of the circuit will become maximum, and the circuit will not allow that frequency to to get mixed into the current, and therefore the circuit will behave like a rejector circuit. So we always say that series LCR circuit is an acceptor circuit at resonance, and parallel LCR circuit is a rejector circuit at resonance. It is always due to the fact that in parallel LCR circuit, the impedance become maximum, and it disallows the resonance frequency to the current of the resonance frequency to be added into the circuit. And in series LCR circuit, we have already studied that at resonance Z, which is impedance, becomes minimum, and as Z becomes minimum, it welcomes the current which is having the frequency equal to the resonance frequency. So that is acceptor circuit, and this is rejector circuit. So parallel, I'll write it down here. Parallel LCR circuit is also called as rejector circuit because it rejects the frequencies, or we can say that it rejects the currents of frequency equal to the resonance frequency of the circuit by maximizing its impedance. Okay, so this is the parallel LCR circuit, and this topic is not included in the boards, but it can be asked, or the questions which are based on this circuit can be, uh, you can see that questions in JEE Advanced paper. So this is an important topic. Don't let it go without going through it. So let's meet in the next lecture, in which we'll be discussing the concept illustration problems. Thank you.